right, welcome to another video. Today is all about exponential equations, and we're going to be going over a couple of growth and decay questions to help you understand how we can set up word problems as equations in order to help us solve for some missing information. When we talk about an exponential equation, we can either have a situation where our value is constantly growing or constantly shrinking. So the most common equation would be like a y equals 2 to the power of x. We have a base value of 2, and it's raised to the power of x. And so what that means is, as I increase my x value, my y value will increase exponentially. I could start all the way at a value of 1, where 2 to the power of 1 will give me 2. But as I increase my x values, you will see that our answers are getting exponentially larger. And if we think about if I were to plug in an infinitesimally small number or an incredibly large negative number, this answer would never be set to 0. Because even if I do like 2 to the negative 1,000, I'm still going to get some sort of positive value as my answer. And that means that we actually have an asymptote down here where our y value is never going to reach 0. On the flip side of things, we have exponential decay, and all that's changed is our base value. Instead of it being a number greater than 1, we have a value in between 0 and 1. And we have a value of 1 over 2, or 0.5 in this scenario. And this is actually going to flip things on its head, where we're probably going to be starting at a high value, and then as x increases, our y value decreases exponentially. And this has to do with how exponents are applied onto a fraction. So let's say I do 1 over 2 to the power of 2. This 2 exponent actually needs to be applied to both our numerator and denominator, which is why we get a 1 over 4. And if I compare that with an x value of 1, my answer would be 1 over 2. So you can see that we're getting increasingly smaller as our x value increases, and that happens exponentially. And once again, just like in the y equals 2 to the x example, we have an asymptote at y equals 0, because no matter what value I put in here, I could put an x equals 1 million. It wouldn't matter. I'm never actually going to reach a value of 0. It's just going to be an infinitesimally small decimal value. So I'm just going to write some of the rules here. If I have a base greater than 1, then I have growth. And if I have a base in between 0 and 1, I have decay. So that's the core difference. All right, so knowing this, we can now represent real-life growth and decay scenarios with an exponential equation if we understand some core values. So this is like the generic setup for an exponential equation. And I just want to go over what each of these variables represent in a real-life scenario. Let's start with the a value. The a value is just our starting value. So this is whatever amount of a thing we start with in a scenario. And I'll give you an example. Let's say we have a colony of ants. And this colony of ants started with a population of 200. So that is going to be my starting value in this scenario. Our b value is going to be what kind of growth or decay is happening. Is our value being doubled? Is it being tripled? Is it being halved? So for this example, let's say that we have a colony of 200 ants and they are being doubled, or their population is being doubled every 2 weeks. So this is going to be our base. Whatever sort of multiplication or division is happening for our original value, that is our base. In this case, it is a base of 2. This represents the general growth or decay in the scenario. The p-value, which is our denominator in our exponent, is going to be how long it takes for our base to occur. So in our example, our base of multiplying by 2 is happening every 2 weeks. So this is basically how long it takes for b to occur. And in our example, we have 2 weeks or 14 days. And then finally, t is just our variable for the overall time that's elapsed. So let's say we have a colony of 200 ants. Their population doubles every 2 weeks, and we've let this population grow for 4 weeks. So time is the total time elapsed in a scenario. And in this case, we've got 4 weeks. So if I were to plug in all of these values into my equation, I could actually solve for what the population total is going to be after these 4 weeks have elapsed. And so instead of just using placeholder values, let's actually go to a setup. All right, a radioactive element has a half-life of 12 days. If 300 milligrams of the element was placed in a container and left alone for 4 weeks, how much is left? So the first thing I want to do right off the bat is write down A, B, P, and T and see how much info I can fill out from the question. So the first thing I notice is we're dealing with a half-life. That tells me that we're dealing with decay for our base, and it's going to be a base of 1/2 to represent half-life. And the element has a half-life of 12 days. What that means is every 12 days, the amount of the element will be cut in half. So if I started with 10 milligrams in 12 days, I will have 5 milligrams. So 12 days represents how long it takes for the decay to occur. So that will be our p-value. Very next thing is our starting amount. It tells us we have 300 milligrams of the element. And how much time total has elapsed? We have left the container alone for 4 weeks. So that will be our total time. Okay, we have all of our values that we need. So I'm just going to write out the generic setup here. Now we just need to plug in all of our values, solve for y, and that'll be how much of the material we have left after 4 weeks. A is 300, B is 1/2. Now for T and P, I want to make sure I'm using the same units. So P is in days, so I'm actually going to change 4 weeks into 28 days, just to make them work with each other. So our T will be 28, and our P will be 12. And so if I plug in all of these values, I should get an answer of roughly 59.5 milligrams. So that is how much of our element is left after 4 weeks. Let's try one more example. A famous chef has 50,000 followers on Instagram. He only created his page 35 days ago, and his follower count was tripling every week. Approximately how many followers did the chef start with? So once again, write out our variable names and fill in all the info we have. So a famous chef has 50,000 followers on Instagram, but in this scenario, this is the final value that he's ended up with. So it actually wouldn't be any of our variables. That is our final value, technically our y value, and that's 50,000. And if I go down to the end of the question here, approximately how many followers did the chef start with? That means that I'm actually solving for A this time. So I won't be able to get that from the question. He created his page 35 days ago. That tells me that this is probably how much time has elapsed. And his follower count was tripling every week. So tripling tells me that this is growth and that our base is a value of 3. And our p-value, or how long it takes for B to occur, is going to be 7 days. And I'm using days instead of weeks just to make my p and t values work with each other. Now, if I set up the equation, actually, this should be a y. I have the final value this time, so I can plug in a 50,000 here. I don't have A, so I'm going to have to isolate for that at the end. B is a 3, T is a 35, and P is a 7. So our exponent here, 35 over 7, we can actually simplify that to 3 to the power of 5. And 3 to the power of 5 will be 243. So to isolate for A, I'm just going to have to divide out this value on both sides. And that should give me my starting follower count that I'm looking for. And I got a decimal. So you can't really have a decimal for followers. You can't have half a follower. So I'm just going to round up to 206. So that means that this chef had 206 followers 35 days ago, and then through the power of exponential growth, he ended up with 50,000 followers after that time had elapsed. So hopefully these examples have given you a better understanding of how you can set up exponential growth and decay equations and how they can help you solve for missing information. Thank you so much for watching, and have a great day.